Hi friends, in this video we are going to see about the problems on design of spur gear. So let us consider the problem. Right, two spur gears are to be used for a raw crusher drive or of a minimum size. The gear has to be designed for the following requirement. The power should be transmitted is 18 kilowatts. The speed of the pinion will be 1200 resolution per minute. The velocity ratio 3.5:1. The tooth profile 20° stub involute. Determine the module and face width for a strength requirement only. Select the material SAE 3245 for both the gear and pinion. So in this problem they asked only about the module and the face width. So we can start the design up to the third step. So what are the given data? Given data. So power is they given 18 kilowatts. Pinion speed they given as 1200 RPM. Speed ratio 3.5. Alpha, that is the pressure angle, as 20° stub involute. Material SAE 3245. Let us go for the step 1, that is identifying the weaker member. So since the diameter of the pinion gear is unknown, so from the table 23.6 I can get the minimum number of teeth required on a pinion to avoid the interference. So for that, from the table, for a 20° stub involute, the minimum number of teeth will be 14 teeth. So I am going to assume Z1 is equals to 16. So we know that I, that is velocity ratio, will be equals to N1 by N2, that will be equals to Z2 by Z1, and that will be equal to D2 by D1. So to find the speed on a gear N2, that is N2 will be equals to N1 divided by 3.5, so I am going to get as 342.857 RPM. So to find a Z2, since I already assumed as Z1 as 16, so I want to find out Z2. So Z2 will be equals to Z1 into 3.5, so I am going to get as 56 teeth. So from the table 23.18 I can get the allowable stress for the given material. So I want to get the allowable stress as 515 megapascal. So identifying the weaker member. So the Lewis form factor have to be taken from the equations. So from the equation of 23.114 to 116. So for that, so y is equals to 0.17 minus 0.95 divided by z for a 20° stub involute. So I am going to substitute the values of Z1 and Z2 over here in the equation. So I am going to get Y1 is equals to 0.110625, Y2 is equals to 0.153036. So I am going to get pinion and gear. So sigma naught 1, sigma naught 2 I am going to substitute in the table, and Y value I am going to substitute. So when I am going to multiply these values, I am going to get as 56.972 for a pinion, 78.814 for a gear. So from this table you can clearly say that the pinion is having the lesser value, so it becomes a weaker member. Whenever the material, same material will be used for a pinion or a gear, always the pinion will be having the weaker member. So the design should be based on the pinion. So coming on to the second step, that is design of a weaker member. So in this you are going to find out the tangential tooth load using two equations. One will be this equation, another will be on the Lewis equation. So let tangential tooth load on a pinion. So Ft is equals to 9550 into 1000 into N CS N1 R1, where N is the power that has to be transmitted, CS will be the service factor, N1 will be the speed of the pinion since the design is based on the pinion, R1 will be the radius of the pinion. So R1 will be taken as D1 by 2. Since D1 is unknown, I want to take that one as M into Z. So Z1 you assumed as 16, so it becomes 8M, that is 16 by 2, 8M. So CS, that is the service factor, so I have to take from the table number 24.13. So for this particular problem I go to assume as AV shock with 2 to 3 hours per day working. So for AV shock, for that 2 to 3 hours I am going to take as 1.50. So that I want to substitute in the CS, that is service factor. Substituting all the values in the above equation, I am going to get that one as Ft is equals to 26,859.375 divided by M. That will be the module in terms of Newton. So coming on to the second one, tangential tooth load by the Lewis equation. So Lewis equation is given by Ft is equals to sigma naught B, Y, P and Kv. So B, Y and Kv will be common. So sigma naught 1 and P will be varying based on the pinion or a gear. So in this case it will be a pinion, so it will become sigma naught 1 B, Y1, P and Kv. So B is your face width, so you can assume between 9.5 M to 12.5 M, that is the module. So I am going to assume as 10 into module. So P is the pitch, so that is circular pitch, so P I am going to assume as pi into module. So Y is the Lewis form factor, so that you have already calculated in the previous step, that I am going to take. Since it is for a pinion, it will be Y1, that will be equals to 0.110625 from the previous step. So KV will be the velocity factor, which will be calculated later substituting the values in the above equation. So when you're going to substitute the values of this in the above equation, I'm going to get Ft is equals to 1789.824 m square into kV. So now this equation or the previous equation which you already calculated over here, that I'm going to substitute both the things, that is equating both the things. So these two equations are going to equate. So I'm going to get the equation as m cube kV is equals to 15. So this is the standard one from which I can find out the module as well as the velocity factor. So to find the velocity factor kV, I need to calculate the mean velocity. So Vm is equals to pi dn divided by 60,000. So d1 and n1 I have taken since the design is based on the pinion. So d1 is equals to m into z1, and I'm going to substitute that, and n1 we already know. So n1 I'm going to substitute, and z1 value I know, I'm going to substitute that. So Vm will be equals to 1.0053 into module m. So for finding the kV, so I'm going to assume a trial and error method. So I'm going to assume the module. So this module you have to take from the table number 23.3, where they will be given the standard modules for a particular case. So in that table, the values will be, some values will be inside the bracket, some values will be outside the bracket. So which are outside the bracket, they are the standard ones that you have to select. So module I want to select the first as 2.5 mm. I want to substitute the Vm formula. So I want to get as 1.0053 into 2.5. I want to get as 2.513. So which is less than 7.5 meter per second. So to get this velocity factor, we have to find Vm. So there are conditions whether it is less than 7.5, less than 12.5, less than 20 or over 20. Based on that, I have to select the equation from 23.134a to 23.138a. So for this it is less than 7.5, so I want to assume this equation as 23.134a, that is kV is equals to 3 by 3 plus Vm. So when I want to substitute the module as 2.5 and Vm I want to substitute in the equation, I want to get as kV is equals to 0.544. So this values I want to substitute in this equation, that is when I want to substitute module as 2.5, kV as 0.544, I want to get as 8.5, which is less than 15, so hence it is not suitable. So I'll go for the trial 2 by taking the module as 3. Again I want to substitute in the value of m over here, so I want to get 3.016 meter per second. So it is less than again 7.5 meter per second. So kV is equals to 3 by 3 plus Vm. So kV I want to get as 0.4987. Substituting this value, so again this equation, that is m is equals to 3, kV is equals to 0.4987. I want to get as 13.46. Again it is not suitable. So coming on to trial 3, I am going to take module as 4. So Vm is equals to 1.0053 m. So m value I want to substitute as 4. So I want to get as 4.0212 meter per second. So for Vm again it is less than 7.5. So I want to use the same formula. So Vm I want to substitute over here. So I want to get kV is equals to 0.4273. Substituting these values I want to get as 27.34. So that is greater than the 15. So therefore I want to assume module as 4 mm. So now I have to check the stresses whether the module selected is suitable for the design or not. So for that I will go for the next step, that is check for the stresses. So first you have to find out the induced stress. So that is given by Ft by By1P. So Ft is already calculated in the second step, that is standardized tooth load. So there I want to substitute the module m value as 4. I want to get as 6714.84. So B value is 10 m. So module I have taken as 4. So it will be 10 into 4, 40 mm. So Y2 already calculated. So Y1 you already calculated, P I am going to get the value of this. So I am going to substitute this values over here, and I am going to get sigma induced as 120.76 Newton per mm square. So calculating the allowable stress for the equation, that is allowable stress I want to go for. Sigma allowable will be equals to sigma naught kV. So sigma naught is nothing but the allowable stress given in the equation, given in the problem. kV value of which you have already calculated in the previous step, that I want to consider. So that I want to substitute over here. If you take the kV, this is the kV you are going to substitute over there. So I am going to substitute the kV. So sigma allowable will be equals to 220.06 Newton per mm square. Since from this two equations you can say that sigma allowable is greater than sigma induced, so the design will be safe. So I can say that the module 4 will be suitable for this particular statement, and the phase width will be 40 mm. So next problem we'll see in the next video.